Today, I'm going to be designing and making multiple prototypes of a knob. Welcome to another episode. The goal of today is to design a knob for this remote control for a model train. This is actually the second throttle that Train Control Systems is going to be coming out with, and I've been doing the CAD work for the case and the knob, etc. Now, the knob, there are two versions of this. One of them is a potentiometer, which means it does not rotate all the way. It rotates less than 360 degrees. The other version, which is this one right here, I haven't printed a case for it, this will rotate continuously. This is called an encoder. So we had this idea that we want this to be straight up and down at the top at the halfway mark so that when you're running trains you can kind of feel where you're at. But then other people said, well, I'd really like the halfway point to be down at the bottom. And so that meant we wanted to see if we could design a knob that would be positionable onto the shaft in either of the two orientations. The first thing I did is did research to see if we could find any knobs like this, and we couldn't, so we decided to go with our own custom knob. The challenge is to make a knob that will fit onto here, and this has what's called a D shaft. This, by the way, is an encoder, and this, what I'm showing right here, is a prototype for a remote control for model trains. So one of the things that I typically do is create prototypes initially with 3D printers, and this actually is a prototype of the actual throttle that works. And so we've been using this for developing the software and testing and that sort of thing. And anyway, in terms of the knob, the way that I did that is I have a screw hole, as you can see here, that goes into a 3D printed section. So I can put a set screw in here and hold the knob in place. And that works fine for, and actually it doesn't fit on because it's too tight. But that works fine for prototyping. The question was then, what do we do for the actual knob? And I did some searching, and the first thing that I came up with is looking at other knobs. A lot of them had brass inserts. So I tried to find a source of brass inserts and was not able to find something, and decided instead to create a design and then get some quotes for it. So let me take you to the computer and I'll show you the design. Here's the knob, and you can see underneath that there's an insert. This is the brass insert. It has two screw holes because you could attach it to the shaft of the potentiometer in either of two orientations. Now, to keep the mold from having to have slides, we need to have the holes so that they're actually slots rather than holes in the plastic part. And if you look at this, you can see that this one is actually at an angle. You have to use a ball end wrench to be able to get in there, but it does work. So I decided to make a prototype of this. I printed out a drawing that has all the critical details. It has this length here, and then these two diameters are the really important ones. So the inside diameter here is 6.05 millimeters. And so I'm going to use a 6 millimeter drill to create the inside diameter. For the outside, I have it in inches, and so I'll just turn it down and try to hit that as closely as I can. This length is important but less important, and this is even less important, that distance. But the chamfer here, the angle, the depth, the length, none of that is really that important. I just need a chamfer so that it provides an entry point for pushing this into the hole. So when I push it into the knob, this will help get it started. I'm going to start by facing off this edge. To keep this from kicking back, what I'm going to do is engage the half nut, and then I'm going to use, after I disengage the feed, I'm going to use this to feed it in so that I don't get any kickback. Now, I'll explain what this is about in a future episode. I basically took the handle off, and you'll see why. Let me set this to 1400 RPM. And then touch off. Okay, so that's taken care of. What I want to do now is pull this out far enough so that I have room for about 1/4 of an inch, plus the cutoff tool width, which is about 0.1. So just to give it some extra space, I'm going to pull it out to, and actually I need some extra space for the knurling as well. So I'm going to pull it out to about there, which should be fine. So that is about 0.6 inches. Okay. So now I'll touch off on the outside. Actually, what I'm going to do is mark it in at about 0.4, which is roughly how far I want to face it back, or not face it, but reduce the diameter. Okay. Come back to here, I'll touch off. I'll set this to 0. And I'll take an initial cut. Let me just check to see the diameter. I'm pretty sure this is 1/2 inch. Yep, 0.49. And I want to reduce the diameter to, according to the drawing, 0.394. So I'll do pull up the calculator. So I said 0.49 minus 0.394. So I have 96 thousandths to go, divide by 2 because the dial is radius, and I have 48 thousandths. So I'll take 20 thousandths to begin with, and then see where we're at. Also engage the feed screw. Okay, let's go. Take another measurement. So that's 0.454. I'm rounding it off to the thousandths. So 0.454 minus 0.394 divided by 2 means we have 30 thousandths to go. So I'll dial in 15 thousandths. That's 10 15ths. And I'm going to use the approach of balanced cuts to see if I can hit it right on, that I learned from watching Stefan Gotteswinter. I hope I pronounced his name correctly. And I'll see if I can provide a clip above or a link above to his video. Now, if I got this right, I should have about 15 thousandths left. So let's measure it again. 0.424. 0.424 minus 0.394. Did I get that correct? Yep. Divided by 2. So we have 15 thousandths left, which is exactly what I thought. So I'll dial in another 15 thousandths, and we should hit it right on. So let's find out. And I'm going to back it off. And let's see how we did. 0.39405. Thank you, Stefan. That's wonderful. Especially for someone who hasn't done much with lathes before and is pretty new to them. Okay, so the next thing I'm going to do is I'm going to take this off because I don't need it at the moment and get it out of the way. I'm going to bring in the tailstock, and I want to first spot drill this. And then I'm going to pull out the 6mm drill and drill that in. Okay, so I'm going to bring this close, tighten it up. Oops, I forgot. It's okay. I caught myself in time. But what I remember now is that I want to knurl it before I drill the hole so that this does not get pinched at all because it's not going to be that thick of a wall. So I'll come back here and I'll put my knurling tool in. Okay, and then you're not going to be able to see this very well, so I'll pull you around to a different camera angle. All right, so what I'm going to do is I'm going to pull this in and get it centered up. And that looks good right there. So the other thing I'm going to do is set the speed lower. So I'll go at 65, I think. And give it a little bit of lubricant. And then just start turning this. And I don't need a lot of knurling on this, so I'll stop it now and see how it feels. Okay, that feels pretty good. So I'll go ahead and, yeah, that looks good. So I'll just take a rag and blot the oil off. Yeah, that'll do just fine. I mean, the purpose of the knurling is to keep this in the hole so that it doesn't come out. And because it's just a test piece, it also doesn't matter too much how good the knurling is. Now, the other thing that I want to do, I'll bring your back around to the other side, is to add the chamfer while I'm at it. Yeah, that'll work. So I'm going to put it back to 1400 RPM. And that's really all it needs. So now I can go ahead and do the drilling. So for the drilling, what I want to do is mark a depth on here. And so I want to go in a quarter of an inch, at least. So I'll do, let me pull this out a little bit. So what I'm going to do is mark this so that we have 0.3 from the cutting edges, not from the tip. So if I go into there, that should be plenty of depth. Okay. That should do it. So now I need to put the hole into here. So I'm going to take this out of the chuck and then take it over to the drill press. I'm going to put the hole in first because it's going to be much easier to put the hole in while I have this whole stock to be able to grab onto with a V-block. And then I'll come back and part this off. I mentioned this does not have to be really accurate. The distance is 0.1 from the end. So I'm going to just, let me bring this around so you can see it. So, that's pretty darn close. Now the other thing I want to do is set it up side to side. And so right now, it's pretty close. The scale is pretty much level, or very close to level. Okay, so it's level right there. So I have a small spot drill. Okay, that looks better. Well, I went a little bit deeper than I intended to, but now at least I can switch to the drill. Try again. I noticed that this moved so that meant I didn't have it clamped down well enough, but you know, this is a prototype, so this should be just fine for the prototype. I almost forgot I need to tap this hole. So I've got an M3 tap here, and I'm just going to tap it by hand, making sure it's lined up visually. And then I should be able to just go through all the way to the other hole. The hole on the other side, I should say. Okay. All right, now what I want to do is I want to get this set up right on the end and then move it in a specific distance, but I want to disengage the feed screw, like so, and then engage the half nut so I have better control over this. And then I'm going to use this to feel when I'm on the edge. Okay, right there. So what I'm going to do now is pull out my dial indicator, put it on here, and then put it up against the tool. Okay, so I've got this locked, as I mentioned, and now I want to set this on 0. Okay, like so. And then I'm going to crank it in to 0.256. So that's 0.5, 0.1, 0.15, 0.2, 0.25, and 0.256. Now I can remove this, put it back where it belongs, or where it lives, I should say. And then we can go and cut this off. And for the cutoff, let's see, I'll run it at, I think, 265. There we go. So it has a small nub on the end, but I can just use a deburring tool to get rid of that. So let me get the deburring tool. And there we go. Nice chamfered edge. I'll go ahead and chamfer this edge as well. And part is done. Here's a knob that I 3D printed. I had to use supports because the outer rim here is not at the same level as this rim here. So I printed it this way, which also gives me a good surface here. So what I want to do is take this and put it in here. And it's a little bit tricky. Because, yeah, 3D printed plastic has some rough spots. Okay, I fool around with this. Yeah, it's not a quick exercise. And it's a little bit tricky. There we go. So you can see it's going in now. All right. It's in there successfully. It did twist a little bit, which is one of the problems that we've had. This is actually the second one that I made. The first one I made off camera. So what I ended up doing is, which I should have done this time, is to put the set screws in first and then press this in place. This whole process of pressing this into place is a manufacturing issue, and this is something that we were concerned about. We did some investigation and figured out that the best way to do this was with heat rather than an arbor press, to have a soldering iron. And the idea is that with the soldering iron, you've got a tip on it that can push down in here, and it's in something like a drill press type fixture. So it'll heat up the brass, melt the plastic just around the rim, and allow you to push that in place. Again, there's the whole question of getting it aligned. So the idea that I had was to put a flat on the insert and then to mold in a corresponding piece in the plastic part so that when you push this in, it will align it. That's a lot of work for them for each knob that they have to assemble. Now that insert is something where I took the drawing in millimeters and I sent it out to get quotes. I tried a number of places. I used Alibaba and got a whole bunch of quotes from China. I also tried getting quotes from companies in the US, and I reached out to a number of different places, got some recommendations, reached out to those people. I was only able to get, well, what happened is I got some replies initially, said, okay, send me your drawing, we'll get back to you. I sent the drawings as well as 3D CAD files. Never heard anything back. It was really hard to get an answer. I finally got an answer from one company. He said he was still working on the quote. And I asked him what the ballpark would be, and he said, oh, on the order of $3 each. Now, this is a part that can easily be made on a CNC lathe with live tooling or some other mechanism of drilling and tapping the holes from the side. So it's not that hard to make. And I was surprised that the estimates were so high. From China, the range of estimates I got were between 20 cents each for a minimum of 1,000 and $1 each. And the middle one, the company that I first tried, which I'd heard about before, was about 50 cents each. So that's a huge difference between 50 cents from China and $3 from the US, from companies where, I mean, there are probably companies out there where I could get it for less, but it's really hard to find them, and it's really hard to get answers from companies, so I'm not sure what the story is, but that was one of the things that drove us to go to China. The next option is one that I found from Adafruit. It's a scrubber knob, and I didn't know whether it was 1/4 inch or 6mm, but I ordered one. This has a very different design. You can see it's completely injection molded, and it has 2 ribs in here that are quite small that fit onto the D part of the shaft. So if I put this on, getting it aligned, it's actually very solid. So I decided to go down this route, and I actually designed a version and sent it to the injection molders. So their concern is that those 2 little ribs, which are quite small, would be hard to keep from breaking off when they pulled them out of the injection mold. That's when I decided to look at another option. And the other option involves, let me show you, these D-springs. And if you're curious, this is the information about where to find more information on these D-springs. So I'll pull one of these out, and they also provided detailed drawings. So I took the drawings and created another test 3D model, which is, I think, this one here. No, this one. So the idea is that the D-ring just pushes into the knob. So this is easy to injection mold. So it just pushes in like that. And then the D shaft again just fits right onto into this spring. And again, it's I don't know if you can see, but it's not wiggling on the shaft. The shaft has a little bit of wiggle itself. So this is the route that I decided to go. And this will be really easy to injection mold. The springs are really cheap. They're only a few cents each. And they're really easy to push into the knob. So this is going to have the best design for manufacturing, as well as very low cost. So this is the route we decided to go. As you saw, I went through several iterations of the design before the final design. And the initial design, using the brass insert, would have been a lot more work to manufacture. It would have cost some money to have them made in China, have them shipped over here, and then we would have need to buy or build a heated insert press that would push the inserts into the plastic by heating them up and melting the plastic around the insert. There was concern about alignment. There was the effort to get the set screws, to have the set screws put into the inserts, just a whole bunch of issues. So the second iteration with the 2 ribs that had would be injection molded would have been a lot easier to manufacture in some ways because it would be pure injection molding, but the tolerances on those ribs were, critical. Getting them right would be kind of difficult. They'd probably have to use EDM to cut the molds for the ribs, etc. So a little bit more difficult to injection mold. The final design that we settled on with the the D-spring is easy to make the mold, easy to injection mold, easy to add the inserts after the fact. The only downside of that final design from the one that we had originally using the brass inserts is that to be able to handle the two different orientations in which we want to put the knob on the throttle, we have to have two different knobs that are in the injection mold. So that will increase the cost a little bit, but that's our choice to give that flexibility to the end user of the product. So we're going to go that route. I'm not quite sure what the increase in cost is going to be. I need to check with the mold company because I'm kind of curious. But I would guess that it's going to be less than the cost of the brass insert. So that's a win. I hope you enjoyed this episode. Please subscribe, give me a thumbs up, comment below, and I'll see you next time.